All right, welcome back to class, gang. Hey, we're going to go over a chapter today, which is called the variability chapter. Um, actually, let me see what exactly your book calls it. Yeah, variability. Okay, that makes sense. Sometimes another word for variability is dispersion. So sometimes you hear that word dispersion. It means the same thing as variability, and variability essentially is how far out or how spread out your scores are within a sample or within a population. So how spread out are your scores around a measure of central tendency? So in the last chapter, we talked about the mode and the median and the mean. Of course, the mode being the simplest and maybe the most crude measure of central tendency, used almost exclusively for nominal data. And then the median and the mean, depending on your circumstances, give you more information. But of course, with the mean, you get the mathematical center of your distribution of your data, right? And so that's the kind of preferred method of central tendency, and kind of like if it's appropriate, then also the preferred method for variability then revolves around the mean. And so we're going to talk about, you know, the different measures of variability, and when to use them. And really, it's dictated by what central tendency you're using. So if you understand when to use the mode, when to use the median, when to use the mean, then you'll know which measure of variability is appropriate for you as well. Okay, so we're going to go over those and talk a little bit about variability in general first, and then we'll dive into the like um, really three different measures of variability. So we'll talk about the range, and then we'll go over the population variance and population standard deviation, and then we'll go over, that's if you're using the whole population, right? Or if your data is just from a sample, so a subset of that population, which is more common. But with a sample, then you have a slightly different way to calculate the variability, or how spread out the scores are around your mean, right? That's for sample variability and for sample standard deviation. Okay, so let me share my PowerPoint with you, and then we'll walk through this together. All right, so the basic idea here, it says measures of variability, the range, variance, standard deviation. Like I said, just like the last chapter, we had three measures of central tendency. We have three measures of variability: the range, the variance, the standard deviation. But really, I want you to think of the variance as a means for calculating the standard deviation. So if you want to think about this as two measures of variability, that's fine with me. That's kind of the way I think about it too, as the variance as a stepping stone to calculating the standard deviation. Okay, there's some new simple notation for this chapter that I want to go over with you, because I'm going to show you two different ways to solve for measures of variance and standard deviation by hand. And there's two different ways to do that. There's something called the definitional formula, which we'll go over first, and there's something called the computational formula, which we'll go over second. I'm going to show both of them to you because I feel like the definitional formula kind of shows you more like why we're using the calculations that we use for calculating, kind of the spread around the middle. And then the computational formula does all the work for you in a much faster way, but you don't really see like the logic behind the formula unless you understand a lot more about notation, right? So I'll show you both. You can use either one. But before we get to that, before we get to any types of formulas, let me just show you some new notation for this chapter. So we talked about sigma in the previous chapter, right? It means sum of. So whatever sigma is attached to, it means add all of those things together, find the sum. So if you see this notation, it's the sum of squared x's, right? So that means, okay, you've got these x values and you've squared them and then you add them up, right? So let's do that first. I'll show you what that means, just like a real teeny tiny, data set, so you can see what this notation means. Real simple stuff. All right, so let me get to my other camera here. There we go. Okay, so we want to find the sum of the squared x's, right? So of course we need to have x's. Let's start with some x values. I'll just plot some down here real quick, just make it real simple. All right, so there's some x values for us. And then we want the sum of the squared x's. Well, if we're going to add up squared x's, we better have some first. So let's square these values. 5 squared is 25, of course, and 6 squared is a 36, right? So, okay, so there's our squared x's. Now, if we just add up this column, that'll give us the sum of squared x's, right? I might as well get it out now. It's my calculator. There's a picture of my kid. Okay. There we go. So we're going to do 25, and you could probably do this in your head, but for those of you that can't, I'm going to go slow, right? 25 plus 25 plus 36 plus 36 equals 122. So there you go, right? There is the sum of squared x's, 122. All right, so there's a bit of new notation for you, the sum of the squared x's. Now, let me show you our next piece of notation. And in this case, it looks very similar, but it's not the same function, right? Because you have to remember parentheses. So our next new piece of notation looks like this. We put a parentheses around that sum of x here, right? We got the parentheses surrounding it. And so that means that we do that first because it's in parentheses. So we're going to add up all the x values and then we're going to square them. And that tells us something called the squared sum of x. So I'm going to share my screen with you again. With my makeshift document camera that I have here at home. And I'll show you this process. All right, so let's use the same data here. We want to get the sum of squared x's now. So let's say we're going to solve for the sum of squared x's. There we go. Oh, I'm sorry. I meant the squared sum of x. That's what I meant to say. All right, so we're going to take the sum of x first, right? Sum of x, that's in our parentheses. So we're going to add up all the x's. So if we do that, right, we'll go real slow. We'll do 5 plus 5 plus 6 plus 6, should give us 22. Very good. So now we could rewrite this as 22 squared, right? So here's our 22. That's just adding up the x values, gives us 22. We plug it into this formula here, 22 squared. So if we do 22 times 22 equals 484. There we go. Now we got both, right? Got the sum of the squared x's and we got the squared sum of x. So even though it looks like, in notation form, if you look at these two, side by side, it looks like it'd be really easy to get them confused. Just, focus on the parentheses and think about your basic math, and you're going to do the parentheses first. Okay, so those two like little formulas there that we do with x, those are going to come in really, really handy when we're doing the computational formulas. Like we'll get to those later, but when we get to those computational formulas, we'll see these formulas again, right? Now, let's talk a little bit more about just variability in general before we move on. Let me erase my little screen over here. There we go. Okay, so we'll come back to these two formulas. Yes. There we go. So here's an example of 3 different distributions: distribution A, distribution B, distribution C. And I want you to notice that for all 3 of these, the average score is 50, right? So, or we can say the mean is 50, right? So we can also see from all 3 of these distributions that they're normal bell curves, right? They're normal bell curves. They're symmetrical. There's a peak right in the middle, right in the center there. We see there's unimodal. And then as you move away from the middle in either direction, to the right or the left, you get a mirror image of each side, right? So we can tell, okay, these are nice bell curves or normal curves, normal distribution. So cool. So that means that the mean, median, mode are all in the same place. They're all a score of 50. But what we want to know is, okay, well, how spread out are scores around 50? And even though they're all normal curves, not all normal curves are the same in terms of variability. So variability is crucial to understand. Let's say that, okay, so here's an example for you. And I'm not trying to display any type of politics to you or tell you what to believe. I always use like attitude toward the president as an example when I teach this class. I've been teaching this class a long time, so I've been through a few presidents. let's say our current president, President Trump, right? And I said, okay, on a scale of 0 to 100, what is your attitude toward the president? All right, well, if we look at distribution A, distribution B, distribution C, even though the average score is the same, it doesn't really tell you how people feel, right? It's not the end of the interpretation, just the average, right? So let's say it's distribution A. That's what we get. This is the attitude we get from, let's say we measured like, 1,000 people, and this is what we found for their attitudes. Be like, oh, okay, well, the average score is a 50, and then the spread around that score of 50 isn't very large, right? It looks like most people are between like a 45 and a 55. Like that's the vast majority of scores. So it's like, okay, well, people are more in agreement of their kind of, what would you say, middle of the road rating for the president if we looked at distribution A. If we look at distribution B, then we can see spreading out a bit more. Now we're going like to 40 to 60 seems to be the vast majority of the data. So there's a little bit more variability. It means some people liked him a little more than in distribution A, but also some people like him a little less than in distribution A, right? So it's really spread out. And then we get to distribution C, right? And then now there's a spread is as large as it gets from 35 to like 65 if we don't look at the tails and the outliers, right? So a bigger spread still. And so that means that, well, it's hard to know what it means. Maybe it means that people have more extreme attitudes. Like we can see that there are lower scores and there are higher scores compared to distributions A and B. But be careful because even though the score is 50, we don't really know how to interpret that average score. It could be that there's people who are right in the middle. We see that score occurring most often. Does that mean, without the measure of variability, we wouldn't know what a 50 means. Like, does it mean that, people hold like mixed opinions? They kind of like both positive and negative, and it averages out to 50 on a 100-point scale? Or does it mean that there were lots of people with positive attitudes and lots of people with negative attitudes, and it averaged out to a 50? You wouldn't know unless you had some measure of variability. So I would say that, if you want to know like the really the purpose of measuring variability, there's a couple of purposes. So I'll write that down here. Like the purposes for measuring variability are really like twofold. One, just in general, to see the spread of scores. And it's not just any spread of scores, but it's the spread of scores around your central tendency. So that in itself on its face is valuable, right? To know how spread out the scores are. But then the second reason is to know, how well your measure of central tendency represents all of the data. So how well does your average score, if it's if you're using the mean as your central tendency, how well does that average score represent all of the scores in that set of data? The more spread out it is, the less it represents everybody's scores, right? So that last graph or set of graphs was trying to show you, okay, if you have an average score of 50, distribution looks like that. Well, the scores are pretty darn similar. But what if you have a score or a distribution that looks like this? You could pretend I drew that normally. We still have an average score of 50. We're doing everything correctly, right? We calculate the average score, we calculate the spread of the scores, but how well does that 50 represent all of the data set? Not as well, right? Just because the scores are spread out more. So it's commonplace. In fact, you're not going to find, a journal article that is looking at descriptive stats and is not going to have right next to its measure of central tendency some measure of variability reported, because you want to know how well those scores or how well your mean represents that data set and just how spread out the scores are, right? Okay. All right. Let me show you one last important thing I think about standard deviation. Like, why do we why do we care about this idea of something called standard deviation at all? So if we have, three measures that we're going to look at today in this chapter: the range, the variance, and the standard deviation. I'm going to bounce back to my whiteboard here for a second. I'm used to doing it this way. We could pretend we're in the classroom together, right? So the idea with the standard deviation is this: if it's a perfectly normal distribution, right? If your data creates this perfectly normal distribution, right? And here's your mean right there in the center. Then that means you've got half the scores to the right, half the scores to the left of this middle marker, right? 50% of the scores here, 50% there. And then the standard deviation, what that tells you is, okay, we're going to rewrite this middle number as a zero. It's zero standard deviations from itself. And then we can go out by standard deviations plus and minus around that number. Don't worry, we'll get to this idea more later on, right? We'll talk more about it. Okay, so why this is important is, let's say here's one standard deviation above and below the mean. So these two areas that I have here make up roughly 68% of all of the data, right? So it's a majority of the data falls within, +1 standard deviation and -1 standard deviation. So the standard deviation is the average distance from the center. And these you would say are the typical scores. The scores that fall in this range, occur with a high probability, just by chance, there's a high likelihood of getting a score within this range. And that's an important thing to know, right? So let me put that in context for you. So if we're talking about something like psychology, let's take psychology and let's take abnormal psychology. So we're talking about abnormal psychology, um, and we're making diagnoses. Then we can say, okay, what is the, I don't know, like average level of depression for people? Let's say that, right? So you're dealing with people who have depression. Well, 68% of us fall within this middle ground here. If we said, let's look at people's depression levels over like 20 years of their life, something like that. Like most of us would fall within this range. Some people, are more likely to suffer from depression than others. And some people less likely to suffer from depression than others over here. But 68% of us kind of have the same reaction. If you think like, okay, what does normal mean? Like there's a cultural definition, of course. Then you turn into like some of my favorite majors, like philosophy majors, where you're like, what's normal, man? Right? Normal by whose standards? Like that's a perfectly legit question. So, some of it is like culture sets the stage for what is normal versus abnormal depression, but also then how do you measure that? And that's where statistics come into play. So there's the statistical definition of normal, and then there's kind of like the cultural, philosophical definition of normal. And they're both important for psychology, of course. But let's say, all right, 68% of the population falls within, these parameters for depression. Some people then are beyond one standard deviation in both directions, right? They're out here a little further. And we go, oh man, if you fall outside of this range, right, in either direction, then over here you're thinking these people have probably diagnosable levels of the major depression, right? And there's not as many of those people, but they do exist. It's not a tiny number. It's just smaller than the general population. And then if you look on the other side, okay, those are people that like don't suffer from depression. Like that's interesting too. There aren't very many people on the other side either. But most of us are somewhere in the middle. So we want to know, okay, what numbers actually exist right at these borders of what is considered like normal or typical, types of behavior. And then what numbers are outside of that. Another example might be this. So I have a buddy who studies aggression, and in some survey research he did, he asked people like, when do you think it's appropriate to respond with, violent aggression? And most of us have the same criteria for when we'll say like that's okay. So most of us fall within this range where we go, there's really two cases that we'll accept violence or aggression from others, and also from ourselves typically, when we'll say it's justified or it's okay. And that's usually when you're defending yourself, right? Or when you're defending someone else who can't defend themselves. That's usually when we say we're okay with that, right? Type of attitudes toward aggression fall within this range is the vast majority of people, which is really good, I think. It makes me feel better. But it's not everybody. Some people are out here in these ranges beyond one standard deviation. Some of us beyond two standard deviations. That's a tiny percent of the population. So over here, they might say, well, it's okay to defend yourself if someone attacks you physically. And maybe they go, it's also okay to act with violence towards somebody else if they just disagree with you. So they haven't done anything to you physically, but you just disagree, and it's okay to attack them. Most of us don't feel that way, but some people do, right? A smaller percentage of people do, thank goodness. And then beyond two, I don't know, these people may be like sociopathic out here, but it's not very many. And so they're like, it's okay to defend yourself. It's okay if someone disagrees with you. And maybe it's okay if someone is just in the way, right? No hard feelings. You're just in the way. Your arm was in the way. I broke it. Sorry, right? You don't want to meet these people in a dark alley, right? Right. Okay. Now on the other side, these are people that are like so anti-aggressive, right? In the extreme end, the extreme pacifists where they go, I wouldn't defend myself or anyone else. I wouldn't ever destroy anything that's living, right? Way out here. That's not most people. And it's also, if we get a little more relaxed, closer toward the center within 1 to 2 standard deviations here, these people might say, well, I wouldn't defend myself, but I might defend somebody else. And the rest of us are going like, defend yourself. Like we approve, right? We're okay with that. You guys chill out, right? You guys can step up. This is where most of our attitudes that are similar lie. And we want to know, okay, what numbers set the parameters for what is considered normal, right? So it's a good thing to figure out standard deviation, figure out what's a typical score and what is an atypical score. All right, so let me get back to my screen here. Let's look at our first measure of variability. The first measure of variability is a real simple one. Your book goes into a little more detail than I'm going to, but we want to look at the range. Most scientific data doesn't use nominal data. You see it sometimes in like sociology, political science, and anthropology. Um, but it's not the most common within the sciences. So I'm not going to go into a lot of detail with this. I feel like we have what's the expression? We have like bigger fish to fry. Is that how it goes? Something like that, right? We have more important things to calculate, which take a little longer. And that's the variance of standard deviation. So I'm going to make this one simple just for the sake of, getting to the rest of the material in the chapter. The idea for the range is just this simple. If you have nominal data or ordinal data, and it doesn't make sense to calculate an average, you're going to use the mode or the median. Like when those are your measures of central tendency, then your measure of variability is called the range. And it's really simple. You just take the maximum score, or the highest score, and the lowest score, which is the minimum score, right? And you just subtract them. You say, here's the distance between the highest and lowest score. So that's a good way to think about variability is distance. What's the distance from the center, right? Um, it's a crude, as you can imagine. You're only using 2 numbers in its calculation. It doesn't tell you anything about the frequency of scores, where they pile up. Um, you're missing a lot of info this way. So you could potentially, make some errors in your interpretations when you're using, a crude measurement for central tendency and a crude measurement for the range, right? But, in some cases, the data you're dealing with is nominal and you're curious about it. So it's the best you can do, right? So use with nominal and ordinal data. Here, I'll show you how to calculate it. It is really simple to calculate. So I'm going to flip back once again to my whiteboard. I'm getting faster at that. The range really is this easy. If you're thinking, it sounds too simple, it is. Just go with it. Enjoy this simple measure of variability. All right, so let's say I've got a few points of data here. something like that, right? Now, the range is just the distance between what's my largest value? 20. That's my maximum value. It's the largest one. And then my smallest one is a 4. So to calculate the range, we just say the distance between 20 and 4 is 16 units. So we might say the mode is this and the range is 16. So it gives you an idea like, okay, the most common score is, right? And then you could say, and the spread of the scores is 16. So the common score is like, a 3, it's spread by 16. You're like, whoa, that's a big spread of scores, right? So there's a lot of scores, high and low. But if the most common score of the mode is a 3 and you go on the range is 2, you go, oh, okay, well, it looks like the scores range between 3 plus and minus 2. So most of the scores, or all the scores in this case, are between a 1 and a 5, right? So not a very big range. So you can get some information, you can interpret it there, but it's not very detailed, right? But that's it. The range is real simple. I don't want to dwell too much on the range in our class. Like I said, we got bigger and better things to do. All right, like the variance and the standard deviation. So let's look at those next. Okay, so the variance and the standard deviation, they have something in common, but they're not exactly interchangeable, right? By definition, and certainly not in calculation and in their utility. All right, so what they have in common is that you use them when your central tendency is the mean. So they both indicate how much scores are spread out around the center point. In this case, the center point is the mean or an average score. So that tells you then you've got interval or ratio data, and it's also a bell curve, right? So right away, you have to have those requirements met. You got a bell curve, a nice normal distribution, and you have interval ratio data. If you don't, then you don't have to bother with the variance and standard deviation. You would report the range instead. So they have that in common, but they are not the same thing, right? Sometimes you'll hear even scientists, which baffles me, use these two words interchangeably, but they're not quite the same thing. So I wanted to kind of, illustrate that point to you. And let's start with, we'll do the population variance and population standard deviation first. So the population variance, I'll read this to you and I'll give you a little demo of what it means. The population variance is the average of the squared deviations around the sample mean. There's a lot of terminology in that little definition, so I'll break that down for you. But let me tell you this: the danger of that is that it communicates a relative sense of variability that can be difficult to interpret. So it's the average distance from the center, which is like the definition for standard deviation. However, in this case, it's the squared average distance from the center, which is a little weird, right? Because why would you want to know the squared average distance from the center? But I'll show you why, right? So it communicates a relative variability, but you have to remind yourself like, oh, that's the squared distance. That's kind of weird, right? Nobody really wants a squared answer. So let me show you an example of this. I'll work this out on my whiteboard for you. All right, so here's just a demonstration of, why this is a relative measure of variability and difficult to interpret. All right, so let's say we're looking at the variance, right? We're going to do it by hand. So remember, it's the average distance from the center. That's what we want, right? So if we were just to go, well, remember, a formula for averages is just the sum of whatever it is you're adding up, right? In this case, I know you don't know this yet, but it would look like that. The average of distances from the middle. So here's the middle and here's a score. So score minus the middle, right? It gives you a distance from the middle. Then you go, okay, we'll add up all of the different distances from the middle and then divide by how many distances from the middle that there are, right? That's how you would figure out just like any old average, right? It just looks a little more complicated. But here's essentially what what this means. So let me create, you don't have to copy this down, by the way. You can put some notes if you want to, if you want a reminder, but I think you'll remember this idea. It's not super complicated. So let's say we have these X values here, right? And if we graph them, then let's do a real simple graph. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then let's see, the frequency is as low as 1. It goes up to 3. So let's do 1, 2, 3 like this. So I'm basically creating a normal curve for us to deal with here. So we have how many ones? We got 1. How many twos? We got 2. How many threes? We got 3. How many fours? We got 2 of those, and we got 1, 5, right? So here we go. There's our bell curve. Right there, we know our average is a 3. And in fact, the mode, median, they're all 3, right? Because it's a nice bell curve. So we can say, okay, in this case, our average score is a 3. Cool. All right, so now if we go back to our annual formula for the average, we'd say, well, what's the distance between each score and the middle? All right, we can see the scores are spread out. So let's take one distance at a time. If we went, 3 to 4, well, the distance is, -1, because we do 3 subtract 4 gives us a -1. Well, that's a little weird. We get a negative number for a distance. Well, anyway, let's keep going. Then we get 3 minus 5. Okay, that gives us a -2. Well, what about the distance between 3 and 3? Okay, that's a 0, right? What about the distance between 2 and 3? Oh, well, now look at that. We get +1, right? And then over here we get +2. So if we just look at these numbers, and let's say we were going to add them up, right? If we add these all up and then divide by 1, 2, 3, 4, 5, right? So we put a 5 there. Well, something you probably notice is going to happen right away, like this negative and +2 just cancel each other out. And the same thing for the ones, negative and +1 cancel each other out. So we're left with 0. So that would tell us the spread around the middle is 0. Well, that doesn't make any sense. Like we can see it. We can see a spread in the numbers. The lowest one scores a 1, the highest scores a 5. So the range is a 4. We know the scores are spread out. How can we get a 0? That doesn't make any sense. So what we do with the variance is we square each value, right? So we would change this formula a little bit and go, let's take the squared values from the center. And we do that just to get rid of the negative numbers. But you can't, only treat the negative numbers. You have to be fair and treat, every single one of these numbers. So we'd square them all, but that's funky because it leaves us with a squared answer. So that's what it means by the variance being, a measure of variability that can be misleading, right? Because you end up with a squared answer. We don't want our answer squared. We want our answer in the same, numerical character as our raw data for it to make total sense. It'd be like you know, let's say give you an analogy. So it'd be like if you're going to go have lunch with your buddy, right? And your friend says, well, where do you want to go to lunch today? And you go, well, it kind of depends on how much money we have, right? Hey, let's make a deal. Let's pool our money together and let's go out to lunch. And you go, I got $10. How much do you have? Right. And your friend says, relatively, I have $81. So you're like, oh man, okay, we can pretty much go to lunch wherever we want, right? We can get something a little nicer with $81. Sounds good. And you go, what do you mean by relative? He's like, well, it's a squared number. You're like, why would you give me a squared number, you weirdo, right? So you mean you actually have $9? That's a big difference between 9 and 81, right? So the square root of 81 is 9. So you're like, okay, why would you tell me a relative number? That's weird. I always think about something like that as an analogy for understanding the variance, difference between the variance and the standard deviation. We don't want a squared answer. We want the answer to be back into its original form. So that's what we're going to do. Oops, let's do this. So that's what it means by it communicates relative variability and it's difficult to interpret. So I would argue you wouldn't want to use these words interchangeably. It's a big difference mathematically, with one of these answers being squared and the other one not squared. It could be super misleading if you reported the wrong one. The scored answer is going to be humongous compared to the actual answer for the spread of the scores. Okay. So the next thing we're going to do is we're going to actually calculate these. And I'm going to make a separate video for each way to calculate this information, just so the videos aren't too long. So I'm going to stop here, and then I'm going to come back, and we're going to work on the definitional formula for population variance and then the definitional formula for population standard deviation. So I'm going to keep these videos a little bit shorter. This is a general idea about standard deviation and variability, and then we'll come back to calculate them in the next video. All right, I'll see you then.